Welcome. Today we begin our discussion on geometric optics. The outline of this presentation is that we're going to first have an overview or a recap of what we've had discussed before, and then see how that which we've discussed connects with what we're beginning to talk about, that is geometric optics. And then we're going to talk about the model of light as a ray. And then finally, we're going to talk about how after having discussed light from the ray model, we're going to talk about the first law that governs the interaction of light with reflective surfaces. Okay, let's first do a recap. At this point, I feel it's always good to recap for the purposes of connecting what we've learned to what we're about to begin. That is, how does this next chapter connect with what we've had a discussion on? So we began with thermodynamics. Thermodynamics is one subject that helps us to understand how energy is distributed when objects are interacting or systems are interacting. And one of the easiest, or rather practical ways that indicate to us the dynamics of thermal energy is the quantity of temperature. We know that when temperature increases, this is an indicator that an object has gained more energy, or there's been a heat transfer to that object. And also when the temperature decreases, we know that the object would have lost energy. Of course, there are other quantities we could have used to talk about thermodynamics. We could have used entropy, we could have used enthalpy. However, temperature is one of the simplest and most practical ways. And temperature, we knew, was an indicator of heat transfer, hence energy gain or energy losses. We dealt with this from a qualitative perspective. That is, qualitatively, when two objects have different temperatures and are in thermal contact, we expect for there to be a transfer of energy, hence also a change in temperature. And also we spoke about it from a quantitative perspective, that we could quantify how much energy is lost in a given object for a certain amount of temperature change. You might remember this from this formula, Q is equals to mc delta T, that the change in temperature of some object with a certain property characteristic would require so much energy in order to undergo such a temperature change. Moreover, not only was a change in temperature an indicator of heat transfer, but also we knew that the changes in temperature could affect the physical dimensions of an object. That is, an object could expand, thermally expand. When you put a glass in an oven and you leave it for very long, eventually the glass's temperature will rise to a point where the glass will expand beyond the forces that are keeping the glass intact, the molecular forces, so the glass will shatter. So this is an effect of heat transfer, that is thermal expansion. This was useful for us because we are interested in learning how objects behave under heat transfer and temperature changes. For instance, a patient, we need to understand how the tissue we are going to expose to X-rays, how does it behave? And also we need to understand how the machinery we're using to perform our exposures will behave under certain circumstances. And we were able to do this by virtue of understanding the thermodynamics. And moreover, we treated the idea of heat transfer, the different media or modes, hence methods of heat transfer. The first one was conduction, the second was convection, and the third was radiation. And in radiographic applications, we saw that conduction and radiation are the most useful ones, because we need to be able to cool down our machinery. For instance, our target atom through which we produce X-rays, we need to figure out a way on how to cool it down. That's why we have some X-ray generators that have a spinning target rather than a stationary one. And those X-ray machines that have a spinning target have a much higher tolerances on heat transfer. We can have higher energy exposures for longer times. Okay, that was the purpose of our treatment of thermodynamics. Once we understood how energy is distributed, that is the dynamics of thermal energy, we then moved on to atomic physics, primarily seeking to understand the structure of an atom. We saw that the structure of an atom dictates its behavior, that is the emission spectra and the absorption spectra. An atom has no choice but to emit according to its structure. It seems an atom emits photons or X-rays or radiates selectively, but this selective radiation is due to its structure. So emission spectrum or spectra is much like the fingerprint of an atom. That is why astronomers can look at the stars and be able to tell us what kind of elements make up that star. That's by virtue of the emission spectra, because a hydrogen atom will never emit in the same way that a lithium atom does. So these become distinct fingerprints of the respective atoms. This helped us to understand what kind of X-rays could be produced, and it helped us to choose the best targets through which we might produce X-rays in our X-ray generators. Okay, and then having understood the structure of the atom and also understanding its behavior under excitations and also de-excitations, we were ready to begin to learn, to exploit what we've learned from nature. So from nature we learn how the atom behaves and its structure. Now we're copycats, learning from nature on how to produce X-rays. Of course, we don't have a sun available to us, which is all the time producing X-rays. We don't have a nebula. However, we do have a lot of electrons on Earth, and we do have electricity. So then we began to talk about the X-ray production in X-ray tubes or X-ray generators. X-ray tubes are nothing more than a machinery for us to produce X-rays. Here we use what we have in abundance, that is electrons and electricity, in order to obtain what we don't have in abundance, that is X-rays. X-rays employ electrons from thermionic emission. Let me repeat that. X-ray generators, they exploit the abundance of electrons from thermionic emission, and then we use electricity to accelerate these electrons, and then on the path of these electrons we place a target, and this target is therefore stimulated to emit X-rays. And it is these X-rays that we use to scan or to expose different anatomies of a human being for diagnostic purposes. Now, what's important is that thus far, from atomic physics to X-ray generators, we were dealing with objects that have electrical charge. Electrons have an electrical charge, so we can manipulate them using electric fields and magnetic fields. However, once we have produced X-rays from our X-ray generators, it is worth noting that X-rays have no electrical charge. So we have no way of manipulating them to our advantage by means of electrical fields or magnetic fields. It is therefore a good point for us to begin to turn and consider the optics. How can we manipulate electromagnetic waves, which are zero, they have a zero electrical charge, to our advantage? How can we manipulate them? And that is the idea behind geometric optics. The idea of geometric optics is rather simple. The subject is very simple. It's geometric because of how light rays behave in the context of when they're interacting with objects larger than their wavelength. We will talk about this later. But the point I want to make right now is that all we will need is Euclidean geometry and a little bit of trigonometry. So this subject, as far as the mathematical side of it goes, is very simple. We only need senior high school mathematics. That's about it. Okay, now we're done with our recap. It's time to consider what is geometric optics. Okay, so far we have had a discussion of light from many different perspectives. We saw that light behaves as a photon. It behaves as a photon when it is interacting with particles that are small in size. When the particles with which light is interacting are comparable to the wavelength of light, light itself seems to have particle behavior. We saw this when we were treating atomic excitation. When a photon would come in, it would strike an electron, or it would be absorbed by an electron, so that the electron itself moves to a higher energy state. There, light behaves like a particle, a photon. There are other contexts where it is better to treat light as a wave, and moreover, light displays wave-like properties. This is in the context of diffraction, but we won't talk about it now. But my point is, light behaves as both a wave and a particle. This is what light behaves like in its nature. However, in optics, we're going to treat light from a different perspective yet again. Here we will treat light as a ray, R-A-Y, as a ray. What do we mean by ray? A ray is a straight line that issues from some point-like source. You might imagine the sun. Because the sun is so far away from us, it basically looks like a point, and the light issuing from the sun reaches us as though it were a ray. That is a straight line stretching from the sun all the way to the earth. That's one way to think of a ray. The key here is that it's a straight line. Light, when it interacts with objects that are much larger than itself or larger than its wavelength, it behaves as though it were a beam or an arrow that begins from the source and reaches all the way to the destination. I should emphasize, it is not that light in its nature is different. Light is still both a wave and a particle. However, those properties are suppressed whenever light is interacting with objects much larger than itself. Okay. The key I would like to again emphasize is that light travels in a straight line as far as propagation is concerned, as it moves from its source to its destination, where it interacts with objects much larger than itself. This is based on experience, slash I would call it experiment. Whenever we conduct experiments, we see that light behaves like a light ray. I'm going to try to convince you of this using a very rather silly example, but consider how do you check your hair? How do you look how your hair looks? Usually you would use some kind of a mirror, primarily some kind of a reflective surface. You might use the screen of your phone if you're away from home, but when you're at home you might use a mirror. It is the reason why we use a mirror is because light travels in straight lines. If light travels, let's say, in curled or curved lines, as indicated by this red line, we might imagine a situation where we could align our field of view with the light ray that's curling from the top of our head and all the way to our eyeballs, to our pupils. The point is, you would not need a mirror for you to see how your hair looks, or the lack thereof of this sketch. The fact that we can never see the top of our head without the means of a mirror or some kind of a reflective surface is testimony to the fact that light travels in straight lines. Otherwise, we could imagine a situation where we would put our field of view in the path of this curved light ray. So this, from experience, is actually not the case. However, we do see our nose, at least part of it, without the need of a mirror. That's because our nose, you might imagine, just let's consider one point of our nose, let's say the point over there. We know that light disperses, it scatters in all directions. We may not see this light ray because this light ray never enters our pupil, although it does cross the field of view, but it's not in the right direction. So we never see these light rays, but this one we see. Actually, this light ray corresponds to what we observe. Again, this path is a straight path. Hence, this is a very silly example, but I hope it helps to demonstrate the idea of light behaving as a ray. By the same argument, you can never see the bottom part of your nose because in this case, a light ray would need to travel in this direction, hence curl. But we never see this. If we were to see the bottom part of our nose, we would need a mirror. So we would need to place a mirror somewhere here so that the light rays coming from here bounce here and then they return to our field of view. So I hope that by that amount you are convinced that the idea of treating light as a straight line, as a ray, is completely and totally justified. Okay, now we are ready to consider the propagation of light. We are comfortable with the idea that light travels in straight lines as a ray would or as an arrow would. So now, what are the different ways that light could go from its source to its destination? The first one is that light could have a free path, a direct path from the source to the destination. So it could have no interaction on its way to the destination. This is basically what primarily happens between the Earth and the Sun, the plants we see around us. Primarily we're looking at them directly, so the light rays from the plants come directly to our eyes with very little interaction in between. They're not interacting with anything around them. And the same is true when light is traveling in a vacuum. There's no interaction with anything else. So light makes a direct path, a direct commute from the source to the destination. The other means through which light could go from the source to the destination is by reflection. The light, in the context of, for instance, the mirror, you're trying to look at your hair, what you need to do, the light that comes into your eyes from your hair actually has had a change in direction. It issued from the top of your head, went into the mirror, or rather reflected from the mirror. So let's go back to our mannequin here. So the light ray from here went to the mirror and then reflected back to your field of view. So that's one way light can go from the source to the destination. So the source is over here, but the destination is over here. And in between, light has changed direction. However, in its change in direction, light has not changed its medium. If you don't understand or you don't appreciate that right now, it will be helpful later on when you will understand it better when I talk about refraction. But the idea is that light here, when it moves from the top of our head to the mirror and then reflected back to our eye, it's traveling in air. The medium through which it's traveling is air. Now, the third way that light could go from the source to the destination is by means of refraction. Here, light both changes the direction of travel, but also it changes the medium in which it travels. For instance, a person who wears eyeglasses. You might notice that this person, the eyeglasses are going to sit over here. The light coming in, even though there were no mirror, the light ray coming in would go from A into the eyeglass and then back to A and then enter our eye. The point is, it has gone through one medium to another. Later on, we will see how light behaves when it passes through a permeable medium. Of course, there are many types of permeable media. For instance, liquids, light shining through water, for instance, and light shining through glass. It could also be traveling through optical fibers. That's how you get your internet nowadays. That's what fiber optics is. It's light traveling inside of an optical fiber. Okay, without getting too distracted, but these are the three ways that light can travel from the source to its destination. The first one is reflection, where light changes direction but remains in the same medium. Refraction is when light changes direction by virtue of change in medium. That is going from, for instance, air to glass, or from glass to air, or from water to air, or reverse. So we will first have a discussion on reflection. But when is this idea of reflection in practice? Where do we see it? Actually, reflection is critical for us being able to see things from different angles. How is it that we can see the same thing from different angles? Here is a simple demonstration. Consider some object with a surface. So this is the object, but this is the surface of the object. The surface is rough, yet reflective. When the light rays come in, they get reflected. Because they get reflected into different direction by virtue of the surface being not smooth, this means the different observers, the red dots correspond to different observers or eyes. So the eye that's over here is going to observe this object from this point, and the eye that's over here is going to observe this part of the object over there, and the eye that's situated there is going to observe this object. That's because the different surfaces are reflecting light into different directions. Actually, the roughness of the surface is what helps us to see the different objects from different perspectives. This is one situation where light, or rather the reflection of light, helps us in our day-to-day life. When light shines or interacts with a rough yet reflective surface. Let's consider the other situation where light is interacting with a smooth reflective surface. Because the surface is smooth, light will always be reflected in the same direction. All the light rays are reflected in the same direction. So, you might imagine shining a light like this using a torch of some sort. Of course, this picture is not as true. It's a little fictional because light would usually disperse wider than this. But let's suppose we could treat it as though it were a laser beam. Now, when light shines on a rough surface, or a smooth reflective surface, all the light rays that are coming in the same angle are going to exit in a different angle. That is, they're going to all follow the same exit angle. That's what I mean by different. It's different from the incoming, but the exit will be the same for all of them. These light rays can only be observed by the eye that's directly in front of them. If an observer is sitting here, this observer will see these light rays. However, an observer who's not in this line of sight will see nothing. Actually, this is exactly what we mean by a blind spot. When you're driving an automobile, because the mirror on your car is smooth and reflective, that means certain things that are not directly within your line of sight will not be visible to you, even though they are there. Hence the need for us to observe our blind spot. The same is true if you're standing in front of a mirror, you see one thing, but somebody who's standing to the side of a mirror, they see something completely different. They cannot see you, usually. That's because those light rays that are reflected from you, or the light rays from you reflected on the mirror, don't make it into the other observer's line of sight. So this is how light interacts with different types of surfaces, or surfaces with different smoothness or roughness. Now we are ready to talk about the law of reflection. Okay, the law of reflection is very simple. It states that the angle of reflection, that is theta r, is equal to the angle of incidence, theta I. Now, we have an incoming light ray and an outgoing light ray. The law states that the angle which the incoming light ray makes with the line perpendicular to the surface is theta I. And this theta I is going to be equal to the angle which the outgoing light ray makes with the line perpendicular to the surface. That's theta R. This is very simple, but I have to emphasize very key things. In order for me to emphasize this, I will use a definition. So this line that's perpendicular to the surface of reflection, or the surface on which light is being reflected, that line is known as the normal. The normal line is it's a line perpendicular to the surface of reflection. Now, we say theta I is equal to theta R. It is important for us to realize that these angles are measured from the normal. It is not the angle with the surface, the light ray makes with the surface. It's not that angle. It's not these angles. These angles need not be equal. But these ones will always be equal. That's how light reflects. Okay. This is our intro to geometric optics on how light behaves, or how we're going to treat light in the context of geometric optics. We're going to treat it as a ray. And after this will enable us to understand how light gets reflected and gets refracted. Our next discussion will be on the law of refraction. So far we have treated the law of reflection. Our next discussion will be on the law of refraction. And if you'd like to fill in more the details, understand more details on this particular discussion, I commend you take a look at OpenStax, chapter 25.1 to 2.2. This will fill in any details that if you're looking for more details, you're welcome to take a look at that. Thank you.